Look at this shape from directly above and ask yourself honestly whether that's really a functioning international airport or something out of science fiction. Because what you're looking at is a golden five-armed structure that genuinely does resemble a starfish. And in 2014, the exact ground it sits on was nothing but open wheat fields. And by 2019, it had become the largest single airport terminal building on the planet. And underneath the entire thing, at this very moment, a bullet train is running directly beneath the floor. Passengers are standing on, and this is the story of how that happened in under 5 years. The deadline for this project wasn't negotiable in any sense because it was deliberately tied to a national anniversary. 4 years and 9 months, no extensions, no flexibility, a fixed date that every single engineering decision on this project had to bend around rather than the other way around. Before a single shovel of dirt was moved for construction, 20,000 people living on the site had to be relocated entirely, and even once that was done, engineers discovered the ground beneath their feet carried a hidden problem serious enough to threaten the entire structure before it existed. This land simply wasn't uniform, and if one corner of a building this size settled into the soil faster than another corner, the resulting differential movement would crack literally everything built on top of it. Dozens of pile-driving rigs ran simultaneously across the site, drilling deep support piles into the ground, and every single one had to be individually verified before engineers could trust it to carry its share of the load above. The design solution to control that settlement risk was almost counterintuitive. Rather than building straight up from ground level, engineers sank 2 complete levels underground first. An entire hidden structure built below grade, before anything visible, rose above the wheat fields. And the reason came down to one deliberate decision made at the very start of the project. Build a single, unified terminal. Building instead of the more conventional approach of several separate terminals, a decision that simplified passenger movement enormously, but created nearly every structural headache that followed. Groundwater fought against the project from the very first day of excavation, and hundreds of dewatering wells ran continuously around the clock, just to hold the water table back far enough for crews to work in dry conditions. But the single hardest problem nobody had fully solved at this scale before wasn't the foundations, the groundwater, or the soil. It was the concrete pour sequence itself for the enormous underground floor slabs. Here's the strange part. A slab of this size can crack entirely on its own from internal stress alone, even with zero external load pressing down on it, purely from the concrete curing and shrinking unevenly across such an enormous continuous area. So, engineers made an unusual call. They deliberately left gaps unfilled across large stretches of the underground floor, sections that stayed completely empty for months at a time on purpose, because filling those gaps too early before the surrounding concrete had finished, its natural shrinkage would guarantee cracking. On top of that, engineers developed a specialized concrete mix engineered specifically to actively resist its own shrinkage as it cured, meaning the project ultimately relied on 3 separate independent defenses against the exact same underlying problem: the deliberate gaps, the specialized low shrinkage mix, and continuous monitoring, because no single solution alone was ever trusted to solve it completely. And in one particularly clever borrowing of ideas, engineers adapted a structural technique originally developed for earthquake-resistant buildings and applied it here to solve what was, on the surface, a purely concrete curing problem. While all of that was happening below ground, an entirely separate high-speed railway line was being constructed directly underneath the terminal at the very same time, requiring 2.5 million square meters of underground piping systems woven through the site, much of it dedicated to a geothermal heating system that lets the building draw heat directly from the earth itself, rather than relying entirely on conventional mechanical systems. To manage flood risk before a single aircraft ever landed, engineers built 2.8 million cubic meters of artificial wetlands around the site, a deliberate piece of environmental engineering functioning as a flood buffer for the entire airport complex. Above all of that sits the roof, supported by only 8 enormous curved columns, and, remarkably, not one of those 8 columns stands straight. Every single one curves, because engineers determined early on that straight, conventional columns simply couldn't achieve the structural spans and dramatic visual openness the design called for. Every individual formwork panel used to cast each curved column was a completely unique shape, no two identical, and inside those curves, placing even a single reinforcing bar even slightly out of position meant it would be permanently locked into position the moment the concrete cured around it, with zero opportunity to correct the error afterward. Before a single roof beam was fabricated, engineers ran 420 separate load scenarios against the design, testing wind loads, snow loads, seismic activity, and thermal expansion from heat, covering every conceivable condition the structure might face over its operational lifetime. The finished roof structure used 38 different beam sizes spread across 170,000 individual structural members, and the Anasi's deliberate decision to minimize the amount of steel used, largely for cost and material efficiency, made fabrication dramatically more complicated because with 170,000 individual pieces, very few of them were identical to one another, and every single one had to fit perfectly into its exact designated position on site. Delivery trucks bringing steel components to the site had to arrive in an order that matched the installation sequence exactly, because getting that order wrong meant work simply stopped completely until the right piece arrived. Building the roof in the wrong sequence risked early sections physically deforming under their own weight before the rest of the structure even existed to support them. The very first roof section was lifted into position as a single complete piece, with 25 more major lifting operations still ahead, and for every one of those 26 total lifts, the exact crane position had to be individually calculated in advance because a crane, positioned even slightly wrong, risked twisting the massive steel section as it rose into the air. 13 major sections were assembled piece by piece at full working height above the ground, every single structural connection checked and verified before crews were permitted to continue to the next one, with the entire steel structure monitored continuously, 24 hours a day, throughout the full assembly process. Any unexpected movement detected by that monitoring system meant an immediate pause across the entire operation. There were 31 separate critical moments where two major structural sections finally connected to one another, and each one of those connections was precisely timed against live deformation data being measured in real time, because the steel was still actively shifting and settling as it went in. Temporary supports holding sections in place were removed, slowly and deliberately, monitored constantly throughout the process, with crews stopping immediately at the first sign of any unexpected movement. Before trusting any of this at full scale, engineers built a small physical replica of the structure and deliberately shook it to simulate earthquake conditions, specifically to observe how it would fail. Because a structure that fails gradually, giving visible warning over several seconds, is fundamentally survivable in a real emergency, while a structure that fails suddenly and without warning is catastrophic. And the entire point of that scale model test was determining, in advance, which of those two failure modes this design would actually exhibit. One engineer, standing beneath a partially completed section, described the steel above him as structurally unable to support its own weight yet at that stage, remove its temporary support even slightly too early, and it would deform permanently and irreversibly. Then came one final structural connection, and in that single moment, dozens of previously isolated steel sections that had existed independently for months suddenly became one single, continuous, unified roof. 2.5 years into construction, for the very first time, the actual starfish shape appeared visible above the site, spanning 180 meters between structural supports at its widest single span, and every millimeter of expected deflection across that enormous unsupported distance had to be calculated with total precision before construction was ever allowed to proceed. With the steel structure finally complete, glass installation began, and almost none of the individual glazing panels covering that roof were the same shape as one another, because the design nobody had fully anticipated posed an entirely new problem. This curved roof structure physically moves as much as 60 degrees in temperature range between winter and summer, meaning every single glass panel and its supporting frame had to be engineered to accommodate that thermal movement without cracking or leaking. The skylights built into that roof weren't purely decorative or purely functional for lighting either. They were deliberately positioned to visually guide passengers through the terminal without requiring a single directional sign anywhere in the building, natural light itself functioning as wayfinding. 5 structural arms extend outward from the central hub, and each individual arm repeated essentially the same complex structural puzzle the central hub had already solved, just at a different scale, and 79 individual aircraft gate positions were fitted out simultaneously across all 5 arms at once, a scheduling and coordination challenge significant enough to require its own dedicated project management structure entirely separate from the main construction program. In a genuinely unusual design decision, engineers stacked departures directly above arrivals within the terminal. Nobody had attempted that particular vertical arrangement at this scale before, and it became a deliberate, calculated choice rather than an afterthought. Kilometers of baggage conveyor belts had to be threaded through corridors and structural pathways that had already been locked into the design months before installation ever began, and none of that infrastructure is visible in any photograph of the finished building, yet every single meter of it had to be fully completed and functional before opening day. Standard fire. Safety code calls for a maximum escape distance of 75 meters to a safe exit point in a building this size. But the sheer scale of this terminal meant some interior points sat 200 meters from the nearest conventional exit, forcing engineers to design and build 29 separate staircases specifically to bring maximum escape distances back within code. Smoke behaves in fundamentally different, less predictable ways. Inside a space this enormous and open compared to a conventional building, and getting the airflow and ventilation design wrong in a structure like this could actually make evacuation more dangerous, rather than safer, not less. At the peak of construction, 4 separate levels of interior fit-out work were happening simultaneously throughout the building, and the daily logistics of coordinating that many overlapping construction teams became nearly as complex as the structural engineering itself had been. In one detail, most people would never expect from a modern airport. Engineers actually built real, traditional Chinese garden landscaping inside the sealed terminal building itself, complete with the same custom mounting brackets that had to be individually engineered for solar panels installed across nearly every section of that same curved roof, because nothing about this roof geometry allowed for standard, off-the-shelf hardware. Over 2,000 individual lighting drivers throughout the terminal automatically adjust in response to changing daylight conditions, all coordinated from a single centralized control system and separately robotic systems, facial recognition checkpoints, and automated baggage handling infrastructure were all installed throughout the building, but none of it actually functioned correctly until every individual system had been fully integrated and could communicate reliably with every other system around it. 293 separate passenger mobility systems, elevators, escalators, and moving walkways were installed throughout. The terminal, with one single moving walkway stretching more than 90 meters in a single continuous run, and once nearly 300 individual systems were physically installed, every single one still required its own individual calibration and testing before being cleared for passenger use. 98% of the components used throughout the entire project were manufactured domestically within China, meaning the supply chains feeding this project had to align precisely with an extremely rigid construction schedule that left essentially no room for delay. Running parallel to the terminal itself, 4 separate runways were under construction simultaneously, an entirely distinct engineering discipline from the terminal building work happening at the very same time. And this became China's first major runway layout actually designed around real projected flight paths rather than simply being fit onto whatever land happened to be available, a detail most passengers walking through the finished terminal would never think twice about because a runway is never simply concrete poured flat onto open ground. One hidden danger drove much of the runway engineering. Standing water pooling on a runway surface can cause aircraft to hydroplane during landing, a serious safety risk at an airport designed to handle roughly 300 takeoffs and landings every single hour, a volume of traffic that required building what became the largest automated air traffic control system ever constructed for a single facility. Every individual in-pavement runway light had to be engineered to survive the physical weight of an aircraft's landing gear rolling directly over it on a daily basis, while still maintaining an exact, precise beam angle for pilots to see clearly. And beneath the runway system itself, engineers built an actual tunnel specifically so that ground support vehicles could cross beneath active runways without ever needing to physically cross an aircraft's path on the surface above. Because northern China regularly experiences dense low-visibility haze, advanced low-visibility landing technology was treated as an essential requirement from day one of the design process rather than an optional upgrade added later. An Airbus A380 eventually lifted off from runway pavement that had been finished and fully verified just in time to meet the deadline, and remarkably, exactly 4 years to the day after the original groundbreaking ceremony, the runway system reached full completion and formally opened, May 13, 2019, the day an actual physical aircraft finally touched down on runway calculations that, until that exact moment, had existed only on paper and in simulation software. Even with the runways complete, the airport still wasn't functionally operational because without cargo terminals and aircraft maintenance hangars also finished, airlines simply had no practical way to actually operate flights out of the facility. In a critical proof-of-concept moment for the entire integrated transportation vision behind the project, the high-speed railway running directly beneath the airport completed its own test run, covering 41 kilometers in just 19 minutes, finally proving in practice that the underground rail connection engineers had built years earlier actually worked exactly as designed. That runway layout, again, represented China's first fully omnidirectional design, built around actual projected flight paths, rather than simply the shape of available land. And it was never just concrete laid on graded ground. Every single layer beneath the visible runway surface was engineered to perform its own specific structural and drainage function. 2,400 floodlights were installed across the airport's apron areas, specifically to illuminate every shadowed area where ground crews service aircraft after dark, because that checkpoint infrastructure and every supporting system throughout the terminal had been engineered from the outset for a facility designed to eventually handle 100 million passengers every single year. At the peak of construction, up to 50,000 workers were on site simultaneously, and across the full 5 years of construction, the project recorded 0 production safety accidents. An outcome that, under this level of deadline pressure, simply doesn't happen by accident, but instead came from relentless, continuous safety enforcement on literally every single shift throughout the entire build. 65 entirely new construction methods and techniques were invented specifically for this project, because the existing engineering playbook, developed over decades on more conventional airport projects, simply didn't cover the unique challenges this design created. Testing a system like automated facial recognition or baggage handling with 10 sample passengers working through it smoothly proves almost nothing on its own. Processing hundreds of real passengers per minute through the exact same systems is an entirely different engineering problem, and teams specifically tested for that higher volume scenario before opening day. But the final, genuinely difficult challenge wasn't structural or mechanical at all. It was operational, because 2 enormous, independently massive construction and logistics projects, the terminal itself and the surrounding transportation network feeding it, ultimately had to function seamlessly as a single unified airport from opening day forward. The airport was formally named a full year before it actually opened, and by that point, some of the genuinely hardest months of the entire project were still directly ahead. Decisions had to be finalized about exactly which airlines would relocate operations to the new facility and which would remain at the existing Beijing capital airport. Decisions that shaped construction priorities and fit-out sequencing across the entire final stretch of the build. Temporary construction barriers. Throughout the terminal came down section by section as different zones reached completion. And for the very first time throughout the entire project, walking through the space genuinely started to feel like an actual functioning airport rather than an active construction site. That final stretch became the last realistic opportunity to catch and correct any remaining problem before the global opening ceremony arrived, with 2,400 floodlights across the apron, ensuring ground crews could safely work around parked aircraft after dark, and every single passenger checkpoint, despite being engineered for an eventual capacity of 100 million passengers annually, had to function correctly and reliably from the very first day of operation, not gradually scale up to that standard over time. Across nearly 5 years of continuous construction, the site crossed one invisible line, almost without fanfare, and simply became a fully functioning international airport rather than a construction project. It became the first hub airport in the world to operate with 100% new energy ground vehicle fleet. Every baggage tug, service truck, and passenger bus on the property running on clean energy rather than conventional fuel. And the surrounding transportation network connects 28 nearby cities within a 3-hour train journey, a scale of ambition that was always designed to make this facility far more than simply an airport in isolation. On September 25, 2019, the very first commercial departure from the new terminal was an Airbus A380 lifting off from ground that had been nothing but open farmland barely 5 years earlier. And on that exact same day, one of Beijing's older airport facilities formally closed its doors for good, one era of Chinese aviation infrastructure, ending at the precise moment the next one began. Seen from directly above today, it genuinely does look like a golden starfish, or perhaps an alien spacecraft that happened to land quietly in the middle of the North China Plain. And honestly, both descriptions fit equally well. What was for years nothing but active scaffolding, structural stress calculations, and endless streams of monitoring data has become, almost without anyone fully noticing the exact moment it happened, simply beautiful.